Well, hello everyone. What I'm going to do here is give you a lesson, basically going over the introduction to our last chapter, which is the calculus of multivariate functions. Topic we're going to deal with is 14.1, functions of several variables. So let's begin. A multivariable function is a function with two or more variables. So you know what a function basically is. You give me an x, I do a calculation, and out pops a y. Well, that would just be the classic Math 141 type of function. But when you move up the food chain, you do a little bit more complicated situations. What we have here is a function of two variables, x and y, and it's equal to this. So you have to give me not just an x, but an x and a y, and these vary totally independently of each other. And whatever these two numbers we happen to be given, then the answer to the function is, in this case, the square root of x squared plus y squared. And you can write down functions similar to how you might write y equals x squared, but in this case, z is very often going to be used as the third variable. If you think about it, it makes sense, x, y, z, right? In this case, the z value is given in terms of the x's and y's. And you can actually move up the food chain here as a function of three variables, x, y, and z, and it's equal to this expression. So there are going to be four main things we're going to deal with in 14.1. And the first one is, how do you evaluate a multivariable function? Pretty straightforward. The second thing is, how do you find and express the domain? Domain usable values of x. Well, how do you define that in a multivariate function world? And how do you visualize them or express them? And the third thing you're going to do, well, basically, we're going to let software do it. And that's, how do you graph one of these? How do you visualize, see a picture of these functions in particular? And lastly, we're going to do a little bit of what's called contour maps and how they can be used. And they're quite useful, contour maps. Again, that's going to be done for the most part using software. So let's move to our first example then. How do you evaluate a multivariate function? Well, here's an example of one. Suppose I wanted to find the value of this function at -1, 2. Well, the position tells you that x is -1 and y is 2. So you just plug and chug. That's pretty much it. And if the function was written, separate them a little bit here. If the function was written in the form, say, z equals, you would probably be given a point or a coordinate. You might want to describe it like that. And essentially, that's your x, and that's going to be your y. And you go here and you plug in the x and y, and you plug and chug. And if you want to do something a little bit more adventurous, you can even do it with 3 or 33 variables. So I don't think there's anything specifically counterintuitive here. I mean, if you want to find the value of a function, evaluating it, you just take the formula for the function and replace all the variables with whatever given values you were asked to evaluate it for. And that is the first one. Now, the second situation is a little bit trickier, but not too much, I don't think. And that is, how do you find and express the domain of a multivariate function? Well, let's look at what a domain is. We're only going to talk about ones where there's two variables here, right? So the domain is no longer going to be the usable values of x, but the usable values of x and y, and R2 just means two-dimensional space. And in this case here, the domain is, well, you just say yourself, what values of x and y can I use in this calculation? Well, since x is being squared and y is being squared, there's really no restrictions. So the domain would be R2. R2 is just another way of saying all real numbers by all real numbers. So let's do one where you actually had to do some work. Oops, there's a function f of xy. Let's keep it in the square root world. And we've got x squared minus y. Now that function will only be will only exist in the real world when x squared take away y is greater than 0, right? And actually, if you want to describe the domain, it's pretty okay. It seems reasonable that you could express it using this relationship. You just have to add a little bit more details. It's called set building notation. So let's see what this extra notation does. Well, you describe the domain as set of all points xy such that, and then you can put your restriction in. And actually, technically speaking, shouldn't that also be allowed to be 0? Because things inside have to be equal to 0. Now, I'd like to, how would I visualize x squared minus y squared greater than or equal to 0? So if we imagine only the floor of your three-dimensional space, so we'll draw it the good old-fashioned flat way. I want to look at this thing and see if I could describe where the points are that are in the domain. Well, if you tell me that x squared take away y is greater than or equal to 0, if I rearrange that a little bit, it's another way of saying it would be that, which is much more helpful. But even more helpful would be to say that it that way. So we're looking for all the points whose y coordinate is less than or equal to x squared. So you would draw the curve y equals x squared. And then you'd think of this as slicing the two-dimensional world into two regions, the region outside it and the region inside. Now, we are interested in the y values being less than or equal to. So how we would describe or show that would be to shade all the places where the y coordinate was less than or equal to the x coordinate. And that would be the visual representation of that particular domain. Another one, suppose I have a function z equals x over x take away y, or make it x plus 1, over x take away y, and I asked you to look at its domain. Well, when it's a rational function, the thing we're really worried about is the bottom being 0. So you do not want x to equal y, correct? Now we want to set that up in set building notation. You go, the domain is the set of all points x, y, such that x does not equal y. So that's pretty straightforward using set building notation. Now, if you want to visualize that, you basically have any point you like, except y equals x. So if I draw this guy as a dotted line, and dotted line in the convention of graphs like this means you do not use points on that line. But I want everything else except it. So basically, the domain is the rest of the universe except that line. Let's do one last one. Suppose we have what shall I pick? No square roots. What's something a little bit more interesting? Okay, let's try this one, which is quite complicated, but it's worth doing. It's version of question 4. I have a function x, y, z, so it's got another dimension to it. And it's a natural log of 64, take away 4x squared, take away 16y squared, take away z squared. Now you want to talk about the domain of this function. You're really interested in what are acceptable values of x, y, and z. Well, a log function must be positive. It's not allowed to be 0. So you're talking about all the points x, y, z, such that this expression is positive. Now, if you want to figure out what does that look like, what you're really imagining is sketching this object and trying to find out which one of the shapes it would end up being. You're just going to take my word for it. This ends up being a 3-dimensional surface, and not only the 3-dimensional surface, it's either the points inside it or outside it. It looks something like this, which is essentially an ellipsoid. Imagine, well, kind of looks like that. And you're interested in basically just describing the boundary. Now, since you want all of this to be greater than 0, technically speaking, it's so the points either inside the boundary or outside. But that's a little bit hard to draw in such a simple picture. And that's how you find and express the domain of a function. The third one is how do you graph it? For instance, that last one I just did, you don't expect me to be able to visualize what the surface of a function would look like, unless it's a very simple one like a plane. What we tend to do is use software. So let me see if I can set that up for you. Right, if we go and look up, we check that you're actually on that, because it has been known for me to think that you're doing something and you're not. And if you go down here, you'll find that we have some essentially 2 different graphing softwares. I'll try that one. So let's suppose I wanted to find out what the graph of the square root. Oops, let me redo that as z equals square. And the square root of x squared plus y squared. Oops, helps when you put the thing in the right place. It's pretty much you let the software take the strain, and what you get to see, I don't need that. There, you see it? It's the surface of a cone, infinite cone going upwards. Now, if I just change one thing, make that negative, wonder what's going to happen. a lot more than you thought. And those little gaps and spaces are just artifacts of the software. They're not there. You can imagine that being a perfectly smooth situation. But the problem why some of these are disappearing is almost certainly caused by the fact that some of these values do not exist as real numbers. So call it Z equals, and we're only interested in 2D ones, so you can do all sorts of cool things. How about this fella? Sine X, hopefully it'll recognize it as a sine, plus a cosine of Y. And let's see what that one looks like. And what you get is a rather pretty model of the sea, I guess. Like, it goes up and it goes down. Is that not pretty? So how do you graph a multivariate function? You basically plug it into GeoBra. You make sure it's Z equals, and then you type in whatever the function is. You can have quite extensively complicated functions. Occasionally you might make GeoBra confused. This is the word. If you make it so complicated, and so occasionally you'll find funny little holes and gaps in it, probably caused by the fact that you asked it to do something that was a little bit weird. So let me see if I can ask it to do something very weird. Right, do you agree that is a pretty interesting function? Aren't there going to be problems at y equals x? So you imagine on the floor y equals x, there is going to be a whole load of explosions. That's my guess. Whoa, now. Can you see that the nice smooth sea-like thing has now been basically destroyed, if I angle it a little bit differently, by an infinite vertical asymptote. Do you see it? And not only is it an infinite vertical asymptote, do you see it's got a little wiggle in it? There'll be a little sinusoidal curve. You could have hours of fun just playing about with that type of question. So what would that look like? And I'm hoping that you actually got to see what I just said. What would that look like if you were going to do it? Let's see. What would that look like? Where's my guy? Oh, in WebAssign homework situation. Right, gotcha. Just getting myself set up here. So the kind of things that you would be asked are, here's a function, tell me which graph it is. It's a pretty typical question. Okay, looks like we're on it. So here is a function, you type it in, and it ends up being one of these guys. They're not maybe the prettiest pictures, but one of these guys would be the same. That one's an interesting blank, but hopefully you'll get it by process elimination. So you could take any one of these and see what kind of function that you would get. The trick ones tend to be the more interesting ones because they tend to have a symmetry to them and they repeat themselves, which is very cool. If I go a little bit further down, kind of jumping around, I know. Yeah. Here is a function. One of these guys, and there's 6, has that graph. And go a little bit further back. Don't worry about these things, these come next. Yeah, that's actually all we have with those. So you've got functions, and then you identify what the graph looks like. And now finished with how to graph a multivariate function using software. So the last thing we're going to be dealing with is called contour maps. And they're very useful because what a contour map allows us to do is to visualize a 3D function, a surface, in 2 dimensions. And you know what contour maps are, I expect, if you've ever looked at an ordnance survey map. Basically, points of equal height are joined together by a curve. So that would represent a hill. And you could imagine that you're flying above it, and some person painted a white line at the 0 feet mark, and then at the 10-foot mark, at the 20-foot mark, and let's say right at top at the 30-foot mark. Can you imagine that that's what you would be seeing as he went round this hill, and every point that was 10 feet, he painted it white. And these are called contour maps, which means that we can use these to visualize what that looked like. If I was going to look at that, for instance, that's what I see. Can you imagine it would be a hill? Something like this. So if you can take a contour map, you can actually visualize reasonably well what the surface of that hill would be. So if someone gave you a shape like a cone, and you wanted to create a contour map for that cone, what you would do is you'd imagine that you were flying above it, looking vertically down on it. And I guess it doesn't matter where you put the thing, but let's say I put it here. And then you imagine what it would look like at a height of 10, a height of 20, a height of 30, a height of 40. And what you would see would be what are called concentric circles. These are circles equally spaced, even if I don't draw circles very well, I clearly don't. And that would be the contour map of this cone. Hopefully that makes sense. It's not a very accurate drawing. It would be nice if we had a piece of software that would essentially take all the strain away. And we do. And I'm now going to set up again, if I can get to the right place. Here we go. I'll please save this time and just tell you that there's a Desmos Contours map link, which I'm clicking on. That way I can be pretty sure that when I go in, that you're seeing it. And this guy does the job. So how do you do the contour map for a function like, f of x equals the square root of x squared plus y squared, right? Well, you don't do anything with the f of x, y, or the z, whatever it's called. You only focus on the formula, and then you are basically ready to go. So here we go. Square root. Oops. Let me tidy this up first before we move on. So you would go square root of, say, x squared plus y squared. And just leave the equals a, because what that is doing is it's doing the heights, like at 1 and at 5 and at 10 and at 15, and it's drawing the thing. Well, there we go. That's a pretty nice looking picture. Now, if you, let's keep some of the quadratic stuff. Let's pin minus there. See what that looks like. Now, do you see the contour map is remarkably different, isn't it? Even although it's just a plus or a minus. So this would be the contour map of Z equals that. But the Z's get replaced by the various heights. Can you imagine taking the shape in your XYZ plane and just slicing it at height 3 and looking at the cut mark on the bit that's left in the top, then cutting it at 4 and cutting it at 10 and whatever numbers you decide in your particular scheme, and generating your contour map that way. Polynomials are pretty interesting, so let's try that. So I'll put that guy in. It's pretty interesting. Let's make this 2. Make this an xy squared, and take away an x. And now if I move this thing around a little bit, that's a pretty interesting, yeah. I guess that's the word I should use. Certainly not what I was expecting, but it's a contour map. It basically, if you know how to interpret it, like imagine you're just looking at the map of some rural area, right? What kind of hill would that look like? And if you could imagine what kind of hill that would look like, starting at the outside and building inwards, and hopefully, I'm assuming going upwards at the same time, and that would be that would look like a hill with 2 spits of land, very skinny and thin and tall, going left and right. And if you approach the hill from the other side, it's much more curved. And if you went upwards, and you have plateau, just kind of here, where nothing much happens. So let's show you what those questions now look like when you do them in WebAssign. And take me a few minutes to get them. We've kind of zoomed by them, but now we can get to see them a little bit clearer. The process is simply just going to be to put it into that software, look at your picture and compare it against the choices, and choose the one that best suits what you see. So for instance, before we do that, let's get this little idiosyncrasy kicked out. Here is a very small contour map of some information, and it says it's day 160 and the depth is 10. So if you do 160 and you do the depth is 10, you're about here. So you might say, well, what number do they want? Well, if you look at the 2 contours, one of them is 8 and the other is 12. So we know it's somewhere between 8 and 12. So your best guess is 10. And if 10 doesn't work, you can try 9 or 11, but it'll be one of those values. Right, now the real question. But this is the guy. One of these guys is going to be your contour map. Actually, I think we did one of them, didn't we? Hopefully, I'll let you remember it. So you would type in x squared minus y squared equals a. Leave the equals a, and the thing's set up to do it for you. And there you go. One of those works. Here's one. One of these is its contour map. Here is a function to figure out A, B, C, D, E, F. That's these guys, and try and match all of these guys to it. Z is one of these fellas here, right? That's the easy one. Now the hard question. Each one of these surfaces has a contour map. And now you have to try and imagine what the contour map would look like of a surface. So I'm going to pick one. See this one with all the nice little bumps going on? To me, it's pretty clearly going to be that one. Can you see why I would choose that? Can you see if you do the slice through that, when you get a whole load of circles? Now, if you took it a little bit lower, when you get a whole load of other circles inside the first circle. Right, now take the shape here. If you did a horizontal slice through it, what would you see? Wouldn't you see a whole load of diagonal lines? Does any of them look like a whole load of diagonal lines? Right. Suppose you, I don't know, some of them you'll get wrong. Some of them are hard to imagine because there's so little information. Right, here's a hill with a valley. You see a hill up here and a valley there? So I want a hill and a valley. I'm trying to think of what one's got it. There's a hill at the right and a valley there. Oh, that one looks good to me. Hill going up the way, valley going down the way. There's lots of symmetry. Let's do it another perspective. What kind of shape would look like this? Well, it's obviously got a lot going on in it, but there's a lot of symmetry in every direction, right? So I'm looking for a shape with a lot of symmetry in every direction and a lot going on. And to me, the one that's got a lot going on, and well, you might not be able to tell it. Oops, go away. It's that one. So you're going to match the function with its graph, and then you're going to match the function with its contour, and then talk a little bit about it. Right, basically the same job again. Function and graph. It's got it. Let's see.